this week's lab session, we investigated how the magnetic force between two magnets changes with separation distance. The magnetic force is a fundamental interaction in physics that describes the attraction or repulsion between magnetic materials. In this experiment, the magnetic force between two cylindrical magnets was investigated as a function of their separation distances between their centers. Magnetic force decreases rapidly as distance increases, and this relationship can often be modeled using an inverse power law. The aim of this experiment was to measure the force between two magnets at different separations and determine the mathematical relationship between force and distance. The apparatus used included two cylindrical magnets, a plastic tube to guide the motion of the magnets, lead sinkers with a mass of 8.3 plus or minus 0.15 grams each, a ruler to measure separation distance, and a stand to support the setup. One magnet was fixed, while the second magnet was balanced against the magnetic force using different numbers of lead sinkers. The separation distance between the centers of the magnets was varied and measured carefully for each trial. To conduct the experiment, the magnets were placed inside the tube so that the magnetic interaction acted vertically. Lead sinkers were gradually added until the magnetic force was balanced. The number of sinkers required for equilibrium was recorded for different separation distances. This process was repeated multiple times to reduce random error and improve the reliability of the results because small inconsistencies in magnetic alignment or friction in the tube could slightly affect the measurements. The measured masses were converted into force using the equation F equals m times g, where F is force, m is mass in kilograms, and g is gravitational acceleration of approximately 9.8 meters per second squared. From the experimental data, it was observed that the magnetic force decreased significantly as the separation distance increased. For example, at small separations, the force was approximately 0.81 newtons, while at larger separations, the force decreased to approximately 0.08 newtons. When the results were plotted on a graph of force against distance, the graph produced a curved trend rather than a straight line, indicating a nonlinear relationship. The relationship between magnetic force and separation distance can be expressed as F is inversely proportional to r to the power of n, where r is the separation distance and n is a constant determined experimentally. The shape of the graph suggested that the force approximately followed an inverse square or inverse power relationship, meaning that even small increases in distance cause large decreases in magnetic force. Several assumptions were made during the experiment. It was assumed that gravitational acceleration remained constant, that the magnets remained aligned throughout the experiment, and that external magnetic fields had a negligible influence on the results. It was also assumed that the force produced by the sinkers exactly balanced the magnetic force. There were several sources of uncertainty throughout the experiment. One major uncertainty was measuring the exact center-to-center distance separation between the magnets, since even small measurement errors could significantly affect the calculated relationship, which is why we used an online attachment to be able to measure the exact centers. Friction between the magnets and the plastic tube may have influenced the equilibrium point, producing slight inaccuracies in the measured force. Additionally, each sinker had a mass uncertainty of plus or minus 0.15 grams, which contributed to the uncertainty in the calculated force value. Despite these uncertainties, the results were relatively consistent and clearly demonstrated that magnetic force decreases rapidly as separation distance increases. Overall, the experiment successfully modeled the relationship between magnetic force and distance and showed that magnetic interactions follow a non-linear inverse power relationship.